Now let's look at these terms strong or weak. Acids and bases can be either strong or weak. A strong acid is what's known as a strong electrolyte. That means that the acid molecule completely ionized into H plus and the anion, the other anion that makes up the acid. A strong base is a strong electrolyte. And sodium hydroxide, for example, when it dissolves, all the sodium ions dissolve and all the hydroxide ions dissolve. Now, weak acids and weak bases are what are known as weak electrolytes, meaning only part of the molecule ionizes. Let's look at a strong acid. HCl is a strong acid. That means that it completely dissociates into H plus and Cl minus. Here's another way of looking at this. We're just going to ignore that for now. And so when we have HCl in water, we have H plus ions, which attach to water ions, which are what these are, and then chloride ions. If we know what the concentration of the acid is, it is equal to the concentration of H plus. Here are some examples of strong acids: hydrochloric, hydrobromic, hydroiodic, nitric acid, perchloric acid, and sulfuric acid. If we were to put a light bulb into a solution, well, not a solution, if we were put into pure water, which is a compound, not a solution, there are no ions in pure water, so the light bulb's not going to light up. But if we put a light bulb into a solution of hydrochloric acid, it is going to light up because there are a lot of ions in the solution to carry a current of electricity. Now, weak acids, on the other hand, really do not dissociate that much. Here's a weak acid, hydrofluoric acid, and only a tiny bit dissociates into H plus and F minus. Most of the molecule, the H and the F, stay together. So therefore the concentration of H plus is much less than the concentration of the HF. And this is true for any weak acid. They don't dissociate very much, so there are very few ions in solution. Here are some examples of weak acids: hydrofluoric, acetic, formic, sulfurous, carbonic, phosphoric, and any naturally occurring carboxylic acid is going to be weak. If we were to put a light bulb connected into a solution that was a weak electrolyte, such as hydrofluoric acid, sorry about that. So we have a weak acid in here, very few ions, so the light bulb is going to light up, but very weakly, because only a small amount of current can pass through because there aren't that many ions. So let's look at how we would determine the concentration of H plus, which is equal to the concentration of H3O plus, in the following solutions. HCl is a strong acid, so therefore the concentration of H plus is going to be equal to 1.5. Acetic acid is a weak acid, so therefore the concentration of H plus is going to be less than 3 molar. So for the strong acid, the concentration of H plus is going to be equal to that of the acid. But if we're looking at a weak acid, the concentration of our proton, or our H plus, is going to be much less than the acid itself. So I'm just going to change this. H plus is equal to H3O plus. So in terms of calculating concentration, if it's a strong acid, it's equal, and if it's a weak acid, the concentration is much less than what is given. Strong bases are going to follow suit. Strong bases will have a hydroxide that completely dissociates. So the concentration of hydroxide is going to be equal to the concentration of the base. However, there's one caveat. We can have a strong base that has more than one hydroxide. Sodium hydroxide just has one hydroxide for the sodium hydroxide, so its hydroxide concentration is equal to the concentration of the base. However, calcium, strontium, and barium hydroxide have 2 hydroxides for every mole of compound. So these are going to have hydroxide concentrations double that of the given molarity. These will have hydroxide concentrations equal to the molarity, and these will have hydroxide concentrations twice that. Weak bases, like weak acids, have concentrations of hydroxide that are far less than that of the base concentration, because only a small amount actually forms hydroxide. Okay, so determine the amount of hydroxide in the following solutions. 2.25 molar potassium hydroxide. This is a strong base with 1 hydroxide for each 1 mole of hydroxide for each mole of compound. Therefore, the concentration of hydroxide is equal to that of the base. Here we have a weak base. Therefore, the concentration of hydroxide is going to be much less than that of the given base. Here we have a strong base, but there are 2 hydroxides. So we're going to multiply this molarity by 2 to get the overall molarity of the hydroxide. Just a quick review. These are all strong bases, the alkali and alkaline earth hydroxides, and then these bases are all weak. Ammonia, pyridine, methylamine, ethylamine, and then bicarbonate. It's not really. Bicarbonate only has 1 hydrogen. Okay.